Welcome to The Explainer. Today, we're going to peel back the curtain on how computers begin to understand human language. And it all starts with what seems like a really simple question.
So here's our roadmap for this explainer. We're going to kick things off with the basics of just counting words. Then we'll see how that idea scales up. We'll look at the simplest way computers try to split up text, see where that falls apart, and then work our way up to the really clever techniques that power modern AI.
All right, let's get right into it with a little counting exercise. Now, this seems like a trick question, doesn't it? And you know what? It kind of is. In the world of natural language processing, or NLP, the answer really depends on what you mean by the word "word."
Okay, let's use this classic sentence as our first numerical example. Take a second, read it over. How many words do you see? So, what did you get? If you counted every single word you saw, you'd get 12. And in NLP, we call those tokens. It's just the total word count. But if you only counted each unique word one time, you'd get 10. We call those types. See, the words the and fox show up twice, and that's why our token count is higher. This difference, this idea of tokens versus types, is absolutely fundamental.
Okay, so that's for one sentence. But what happens when we scale this idea up from a single sentence to literally millions of them?
Well, see, AI models don't just learn from one sentence at a time. They learn from something called a corpus, which is really just a fancy word for a huge, organized collection of text. Think of it like a massive digital library. And as you can see here, we're talking about an incredible scale. Just to give you a sense of what we're dealing with, a corpus made of social media posts can easily hit 50 million tokens. That's 50 million individual words for the computer to count and analyze.
So how does a computer actually do all this counting? Well, the very first and most basic method is surprisingly simple, especially if you've ever used a command line.
It's a classic three-step move. First, the computer basically isolates every word by knocking it onto its own line. Then it sorts that whole big list alphabetically. And finally, it goes through and squishes all the identical words together and just counts them up to get a frequency list.
And the result is a pretty cool transformation. You go from that jumbled, messy list of tokens on the left to a perfectly clean, sorted, and counted frequency list on the right. Now you know exactly how many times each word appeared. Simple, but effective. But, what happens when our text isn't a nice, clean play? What about messy, real-world text? Well, this is where that simple model really starts to fall apart.
Think about it. If we just split words at spaces and strip out all the punctuation, we lose a ton of critical information. MPH becomes 3 separate letters, M, P, and H. The dollar sign in $45.55 just vanishes. A URL or an email address, they get completely mangled. This simple approach just isn't smart enough for the text we use every day.
Okay, let's really throw a wrench in the works. How in the world would any of this work for languages that don't even use spaces between words?
Take this sentence in Chinese. There are no spaces to guide us. None. So how is a computer supposed to know where one word ends and the next one begins? The whole idea of what a word even is suddenly becomes really fuzzy. And you can really see the problem right here. This same sentence can be logically split up in a bunch of different ways. We could group the proper nouns together, which gives us 3 tokens. We could break it down into smaller, more granular pieces, which gives us 5 tokens. Or we could just treat every single character as its own token, giving us 7. Each choice creates a completely different numerical starting point for our analysis.
So, to solve all of these problems, modern NLP uses a much more elegant solution. Instead of trying to break words down, it actually builds them up from tiny pieces. This whole idea is called subword tokenization, and a really common way to do it is with something called Byte Pair Encoding, or BPE. It's a data-driven approach. It starts with the smallest possible units, individual characters, and then it looks for the most common pairs of characters that sit next to each other and merges them into a new unit.
Okay, let's watch this in action. We start with this small collection of words. Our initial vocabulary is as basic as it gets. It's just every single individual letter in our text, plus a special symbol that marks the end of a word.
So first, the algorithm scans through all the text and counts up every pair of characters that are next to each other. In this case, the most frequent pair is E followed by R. So the algorithm merges them into a brand new token, and adds that new piece to our vocabulary. And then the process just repeats. The algorithm scans everything again, but now the most common pair is our new token, followed by that end-of-word symbol. So they get merged together into a new unit, underscore.
And we go again. This time, the most frequent pair is N and E, so they get merged into Ni. This goes on and on for thousands of steps, building up a vocabulary of the most common and meaningful pieces of words. And this is why it's so powerful. Because BPE builds from the ground up, it can handle words it's never seen, it can handle typos, it can handle new slang. It's just a really elegant solution that it learns all by itself directly from the data.
So we've gone from a simple counting problem all the way to a sophisticated system that can literally learn the building blocks of any language. And that brings us to a final, pretty fascinating question to leave you with. If computers understand our language using all these little pieces, then what really defines a word anyway?